Are you? Can you go now? Are you ready? Okay.
Yes, I am.
So Alberto Ramirez, he's with Well Data Labs, and he's going to talk about this a workflow and a model that uses machine learning to recognize events in time series fracturing data. I'll let you go ahead and get started with that.
All right, let me share my screen here. Can you guys see my screen?
Yes.
Yeah.
Okay. So thank you all for staying to my presentation. My name is Alberto Ramirez. I'm a data scientist at Well Data Labs. And I'm gonna present to you our event recognition on time series frag data using machine learning. So here's an outline of the presentation. I'm gonna do a frag data overview, talk about time series frag data, event labeling, and what's the problem and how our solution benefits operators. And then I'm gonna talk about machine learning event recognitions. I'm gonna briefly go through our methodology, and I'm gonna see if we have time. I'll explain two cases: the start and end time event recognition and the ISID, also event recognition. And at the end, I'll give you some takeaways of this presentation. So if you're not familiar with time series frag data, this is how it looks like. You have here in red the pressure, you have here the slurry rate, the clean volume, and the propan concentration in green. And this is a stage, and as you can see here in the back, this is your whole well. So for every well, you have multiple stages, and here's how they look like. You can also have 30 plus additional data channels from multiple sensors in the field. So here's what on the stage how engineers have to manually label events in order to get consistency on their data. So first they start with the start of the stage and the end time of the stage. And then you'll see here the breakdown pressure, the dibetter, if there is one dibetter, of course, and the ISIP at the end of the stage. So this is the process right now, how engineers are labeling this type of events. And the problem here is that this process is very time-consuming process. So think about multiple wells with multiple stages. You're gonna have people labeling all these stages throughout the day. And if you have multiple crews, then 2 or 3 engineers will come and label these events. And that might be inconsistent because one engineer chooses a way to label events and other engineers will choose another way. So what we're trying, the problem here, it's a time-consuming process, and it's also a very inconsistent process. So our solution for this problem will get rid of the time, because we're gonna automate the selection or the labeling of these events, and also we're gonna bring consistency to this process. So if you have your well, and all of the stages will be labeled using machine learning algorithms. So here's our methodology and how we have been working in Well Data Labs with the data that we have. So first, we've gathered the data from our cloud-based platform. And we start by cleaning the data, getting rid of NAs, things like that, making sure that we have all the data we need. What I mean is the channels of the treating pressure, slurry rate, bottom hole propan concentration, clean volume, all of those channels. And also check the frequency of the data. We usually work with 1 second data. So our files are like really huge. So every row, it's 1 second. So for per row, you're gonna have a treating pressure value, slow rate value, and all the other values that are important to this analysis. And then we clean up those data sets. We usually gather data from different formations in the United States or different operators in order to build our models, because we have access to our clients' data. And once we have that, we start either extracting features or creating new features that could be first derivative, second derivative. Just we want to help the algorithms on the training process. I know sometimes, and it's believed out there that some of the neural networks, they don't need this type of feature engineering before on the training data, because eventually the algorithm will do it. But we like to help this algorithm that in order to get, basically we're getting better predictions out of it. So once we have our data set, we divide the data set into training, validation, and test. So our training data, it's the one that we tag. Our validation data will be all other stages, part of this whole data set. Very similar to the training data, and this is they're used in order to validate which algorithm we're going to use or finally use for the problem that we're solving. And then the test data comes from, like, it's data that the algorithm has never seen, and it's basically the one that allows us to get the accuracy, the real accuracy that we need in order to show that we're coming up with a good solution. So once we have divided this training, validation, and test data, one thing I have to make clear, we use multiple wells, and we use multiple stages. So we try to select stages for the training data. We try to select stages from the heel, from the toe, and from the middle of the well. So we have a very diverse data set, and we don't have a bias. We don't introduce bias to the algorithm. So once we have those data sets divided, we start training the algorithms that we think will give us a good result or prediction out of the data. And that's where we start. Once we have some solution, we come up with problems or stuff like that. Then we start to changing the parameters or something called hyperparameter tuning, especially for artificial neural networks. That's when we start making changes to the model, and based on the training and validation data, we try to improve the accuracy of the model. So once we test it at the end, once we have this algorithm selected, we test it using the test data, and that's where we get our predictions and our accuracy. So in Well Data Labs, we have this idea that it comes from product, and it's just to try to find a minimum viable product. So every time we're trying to come up with a solution to a problem, we try to make it like a small project, and then from that, if everything goes well, then we start adding new stuff. So an example for one of these cases is that we started with like pretty good stages, like you can call it by the book. The behavior is very normal. And then we start adding more and more stages with problems. As you can see here, the treating pressure goes up and down, goes up and down. And then finally the stage starts. And then we keep adding these type of stages with, like, they seem a little bit more difficult. So the algorithm will be trained to recognize all of these stages. And then at the end, as you can see here, this is a very bad stage, but we use it to, as I said before, make better predictions out of our models. So our first case of study, it's the start and end time labels. For this project, we use logistic regression as a classifier. We thought about this project as a binary classification project. I'm going to talk about that later. But we selected logistic regression out of multiple other algorithms, machine learning algorithms, because it's a binary classification problem. It predicts probability of an instance belonging to a specific class. It works better with data attributes that are not correlated, and it's easy to train. It doesn't take a lot of time when training, and so we can do multiple. We can make multiple changes in order and retrain our algorithm, or even add more training data, and it won't take a lot of time to train. So here's an example of how our training data looks like. So as you can see here, we tag the data with zeros from the start of the file, or the start of the file to the start of the stage. And then we tag the data with ones from the start time to the end time. And then we tag zeros again up to the end of the stage. Depending on the operator, or depending on the company, they will have different selections of the start time. Some people will start earlier, some people will start later. Same with the end time. Some operators get here when the slurry rate goes to 0. Some operators, they want to see the whole file. So for this case, we decided to go where the slurry rate starts and where the slurry rate ends. We are able to retrain this algorithm in order for another operator that will like different, or would have different selections of start and end time. So here's how our training data would look like. As I said before, we have training pressure, slurry rate, and clean volume per second. This is per second data. And then here's how we tag the zeros and ones. So zeros up to the start of the stage, ones, this is just an example. This is not the whole data set, but it's just for illustration purposes. We have zeros, ones, and then zeros again. So our prediction will look like this training data will train the algorithm, and we validate it. We have a high accuracy. So now we're happy with the algorithm. So now we grab the test data and pass it through the algorithm in order to make predictions. So for this case, the algorithm will predict also zeros and ones, are very similar to this training data, the start and end time. And what we do is we calculate the difference between ones and zero. I think I'm missing that file. But just basically calculating the difference between rows. So 0 minus 0 will be 0, 0 minus 1 will be minus 1, and then 1 minus 0 will be 1, and then 0 minus 0 will be 0. So at the end, we get a column that looks like this one, and then whenever we have ones, that's the start time, and whenever we have minus 1, that's the end time. So here's how a prediction will look like. So and here's this prediction is straight from our app. You have the start time here, the beginning of the slurry rate, and you'll have the end time here. Depending, as I said, on the operators, they will have different start and end times. But for our case, we were very happy with the predictions that we were getting. I think for the start time, we were around 90% accuracy, and for the end time, we had around 95% accuracy. So our second case of study is the instantaneous shutting pressure, or ISIP. Here's a definition of the ISIP. it's the final injection pressure minus the pressure drop due to friction in the wellbore and perforations of slotted liner. As you can see, this happens at the end of the stage, and it's just basically because of the signal, the treating pressure signals behave like this because of the water hammer effect. And then you want to calculate the ISIP being the pressure, the instantaneous shutting pressure at the end of the slurry rate, or where the slurry rate is equal to 0. There, as I said before, there are multiple ways that different engineers will calculate this ISIP or pick the ISIP from the stage. The way we did was we try to recognize, we used a couple of algorithms. The first one, it's a neural network that will try to recognize out of the stage. It will isolate this area, the area that you're seeing here in the circle. And then we use linear regression in order to find this point where the slurry rate is equal to 0. And then we select the pressure point at this exact moment. And that's where we get the ISIP value. So for these projects, as I said, we use a neural network with 3 input layers, 3 hidden layers of 2 nodes each, and 1 output layer. Here's a quick explanation of how a neural network works if you're not familiarized with that. It basically randomly weights the initialization for all the nodes, forward propagates the calculated to calculate an output, and then compares the output to the training data, measures the error, and goes back, doing backward propagation to every node, and then calculates the weight error contribution and adjusts accordingly. And this is repeated until it gets a final solution. For this, we also treated this project or problem as a binary classification problem. So we tag zeros from the beginning of the stage to almost the end of, or where the slurry rate is equal to 0, and then 1 in order to isolate that area that we were looking for in the ISIP. That includes the water hammer here behavior, and then zeros up to the end of, or where the pressure keeps going down until it reaches basically 0. Once we isolated that area, we apply a couple of filters that will filter outliers, and then we isolate. Once we isolated that area, we use linear regression and extrapolated linear regression up to the 0 rate time point, and finally got an ISIP value. So for the results of this project, the algorithm was trained with a 90% accuracy, which is a really high accuracy for our algorithm. We tried to add multiple stages to this training data, so we'll have we have good predictions, a good algorithm, a good neural network to predict the ISIP value. One thing that where we found problems was when the treating pressure was under 2000 psi, and when the treating pressure was above 8000 psi. So for those cases, we added more training data that helped the algorithm make better decisions on isolating the specific area we were looking for. And then it's just a linear regression that calculates the ISIP value. For the test data, and we've been testing this in multiple operators and with multiple wells, the predicted flags were within 72 psi average and plus or minus 35 psi median of the manually selected flag. As you can see here, we use subject matter experts that will manually select the ISIP value from all the stages, and then we compare our predictions to their selection, and they were really close. So we were happy with how the algorithm performed, how the neural network performed, and how the model basically performed while we were offering this. So some takeaways from this project: and classification techniques generate accurate predictions to flags events in high-frequency fracture impulse data. So this is very important. It's not only applying just a classifier there and see what comes, what prediction comes out of it. We try to, once we are like cleaning our data, and we try to come up with features, and we relied a lot of feature engineering in the company, and on other projects that we have worked before up to now uses only feature engineering to make predictions, and try to, like, we're trying to replicate how an engineer or a subject matter expert will select some of these events that we're showing here. Not for this case, these two cases were pure machine learning. But what I wanted to say is that you'll have to work on your training data. You have to make sure that you're selecting multiple stages from multiple wells in order to get not introduce bias to your training data, and also to get better predictions out of your algorithms. The second one, it's accurate flag selection makes processing large volumes of fracture treatment data viable and reduces time spent reviewing field data for quality control. As I said before, the whole goal of these projects is to automate this event labeling and to bring consistency to the data for each operator. So and now the engineers, instead of spending time labeling all the stages on every well, especially if you have like multiple wells, or if you have legacy wells that you want to label in order to use them for any type of research, you don't need to have a person doing this manual event labeling. Now, with the touch of a button, it's just, it will run the algorithm and select and will label all the events that you need. And then finally, iterative model development allows us to start simple and build a model as we learn from it and the data. As I said before in one of the slides, starting simple with some type of stages that will give you good accuracy, and then try to, once you can retrain your model, to add more and more of these stages that are not like by the book stages. That will give that will be one of the or I wouldn't say the best way to do it, but it's a way that we have been using here in Well Data Labs, and it's been working very well. So we are happy to share with you guys how our process or our workflow is right now. And I think that concludes the presentation. Thank you for listening to our presentation. And if you have any questions, please.
Do we have any questions for Alberto? You ready? So, okay. That's interesting. Hey, and maybe I've missed it. Have you guys deployed this much yet? Is it where you're at on the deployment phase?
Yes, these two cases are deployed in our app. They work, as I said, when you have your stage. Like every operator will have their account, and once they will have this list with models that they can use on their data, and just by clicking on one button, all the stages for a specific well will be processed, like in batch processing, and it will label all the events that the operator needs.
Okay. And then as far as time, how long does it take to actually develop a training data set and train the algorithm?
So depending on the access to your data, through Well Data Labs, we have access to a lot of data from multiple operators, so that helped a lot. But we're talking about from the start of the project to the end of to where you finally have the code for deployment. I'm not counting the deployment here. We're saying between testing and training and testing, we're talking about like 12 weeks or more.
Oh.
It's not an easy process. It's not a quick process because, as I said before, you're gonna start. Sometimes the algorithm works for one type of wells or one type of stages, but then you get more and more stages, and that's when everything goes not as good as you planned it.
So then would you retrain the algorithm?
Yes. What we do is at these stages that seem to be not working well, so we retrain the algorithm and come up and grab new stages from new wells and test it again. The retraining part, and especially the modification of the parameters, that takes a while. But once you have those covered, and as I said before, the feature engineering helps a lot the algorithms to identify those events. That's when you're ready now, and then you can deploy it in the app. So for the app deployment, what we try to do as data scientists is build the code like it's a deployable code. And once we have that done, we have also the application has a really nice UI that lets us just upload the code and connect through APIs to the data and show the prediction to our customers.
Okay. Any other questions for Alberto? Okay. Well, thank you.